This is the final talk of our day, and thanks for sticking around. And it's going to be given by Lea Santos of Yeshiva University. And she's going to talk about indicators of many-body quantum chaos and time scales for equilibration.
Okay. So first, I'd like to thank Shiridan for this invitation and you all for showing up. So the results I'll show here were obtained with the previous postdocs, Jonathan, Marco, Mauro. Jonathan is a main collaborator nowadays, and also other collaborators, and you'll see their names showing up in the next slides. So the plan is I'll first start talking about the several indicators of quantum chaos. As you know, quantum chaos had this peak back in the 80s, 90s, but now since around 2008, the subject has revived, mostly because it's very much connected with some hot topics. For example, thermalization, isolated systems, the problems about localizing a system with interactions, and the issue of the out of time order correlator, which may be or not a dynamic indicator of chaos. I'll talk about these three topics, and there are of course others like quantum scars, which I'm not going to talk about. So I'll start talking about indicators of chaos that are associated with static properties, and then those that are associated with dynamics. And at this point, I'll really mention what I'm mostly interested in which is non-equilibrium quantum dynamics. And here you'll be seeing the spectral form factor that has been talked about here, but really in the context of dynamics, not just analysis of level statistics in the time domain. So the main questions that we are interested in when studying dynamics is really what are the time scales involved in the relaxation process of these isolated many-body quantum systems. It's clear, or we sort of understand when they thermalize or equilibrate and thermalize, but how long does it take to reach that point? And what are the different behaviors that we find along the way, different self-averaging properties, okay? So anyway, let's start with the most popular static indicator of quantum chaos, which you have heard a lot about, like the distribution of space in between neighboring levels, the level spacing distribution. So going back to Wigner in the 50s, he was using random matrices to describe statistically the spectrum of heavy nuclei. Now, matrix is filled with random numbers. The only constraint is to satisfy the symmetries of the system we are trying to study. So in the case of heavy nuclei, he was mostly interested in matrices that are real and symmetric, those from the Gaussian orthogonal ensemble. And these are the ones that I'm interested in here. The realistic systems that we are going to study are described by real and symmetric matrices. But very well, if we come back to the level spacing distribution, as you already heard, when you're dealing with random matrices, you get a curve that looks like this red one, which is the Wigner-Dyson distribution. So no spacing is close to zero, no degeneracies, now you have level repulsion. You have the eigenvalues are correlated. So that's the key word, correlation between the eigenvalues, rigid spectrum. All right, so simple idea that worked super well. Here you have data from real nucleus, and the idea was extended to other complex many-body systems, atoms, molecules, and so on. Of course, full random matrices are not physical. They do not describe any realistic system. Of course, Wigner knew this very well. Wigner introduced what is known as band random matrices, which are random numbers that you have only within this band. The problem is that when you go away from full random matrices like this, it starts getting hard to get analytical results. But there is a zoology of different kinds of matrices that bring us closer to realistic systems. Here, I just want to mention for this audience, they serve the two-body random ensembles. Now, the two-body random ensembles are described by matrices like this. So you have the one-body term with random numbers here, the two-body terms with random numbers as well. You can use bosons here or Fermions. So this is the kind of model, very realistic, and has been used by practically everybody in the quantum chaos community. This kind of model is equivalent to what is now known as SYK model. And why I'm bringing this up? Well, of course, the questions that were asked under the name of two-body random ensembles may not be the same questions asked under the name of SYK model, but realizing that these things are equivalent may be beneficial for both sides. In the context of two-body random ensembles, it's true a lot of emphasis in level statistics, because that was the question at the time, nuclear physics. But that's not all. And there are analysis of structure of eigenstates, and there are several studies about dynamics also, like growth of entropies, and Israelev, Flambaum have worked in this direction. Up to this point, I'm just talking about many-body systems. Where does the story of chaos come into play? In another context, in the context of systems with few degrees of freedom, for example, billiards. So what people realized, when the billiard in the classical limit was chaotic, then in the quantum domain, the levels would follow the Wigner-Dyson distribution. On the other hand, if it was regular in the classical limit, then in the quantum domain, you could get distributions such as this dashed line, Poisson distribution, telling us that the levels can cross, that the levels are no longer correlated. So this established this relationship between classical chaos and level statistics. And so what people used to call quantum chaos was just signatures that you would find in the quantum domain that will tell you whether the system in the classical limit was chaotic or not. So this is well established for systems with few degrees of freedom, not yet for for systems with many degrees of freedom. One of the main problems there is to do the semi-classical analysis, now these many body quantum systems where you have this proliferation of periodic orbits. In this talk, I'm going to take an easy path, and whenever I see a Wigner-Dyson distribution, I'll say that my system is chaotic. Okay, so whenever you hear the word chaotic, that's what I mean. Now, we'll be talking about spin half systems, spin systems. One example for Hamilton is this one. This is spin half, one dimension, couplings between nearest neighbors. So this is what is known as XXZ model. So in 1D, it is an integrable model in the sense that it's solved with the base ansatz. But there are many, many ways that you can break integrability and get a Wigner-Dyson. For example, if you add couplings between second neighbors, or if you add on-site disorder. This Hamiltonian here with on-site disorder is the one used to study many-body localization. And why does it get so hard? Because with interaction and disorder, the interplay between the two brings the system into the chaotic domain. So the eigenstates become very spread out. So you need a strong disorder to finally localize the system. Okay, but let me be more precise here. Once I get a Wigner-Dyson distribution, according to my definition this talk, am I done? Can I just say, okay, my system is chaotic? Let me add one word to this story, and the word that I'm adding is like robust. Okay, because we can construct an integral Hamiltonian, which would show statistics as in random matrices. This has been done. But these situations are very delicate. Now you change the parameter of the Hamiltonian slightly and you lose the Wigner-Dyson distribution, so it's not robust. Another scenario where you can get Wigner-Dyson distributions is, for example, in tight binding models, like the 1D Anderson model that we all know is a localized system, no interaction here. Well, if I study a finite system that is smaller than the localization net of the system, I get a Wigner-Dyson, but again, it's not robust. No, it's just a finite size effect. Increase the system size and you lose it. Okay, so robust Wigner-Dyson distributions is what I'm going to be, the idea I'll be using here to say the system is chaotic. Let me mention another detail in this story about the Poisson distribution. If we get a Poisson distribution, are we guaranteed to have a chaotic system? Oh, sorry, an integrable system. And in the other way around, if I have an integrable model, should I always get a Poisson? So again, we have to be careful. No? And Victor already mentioned that. No? Suppose I have a chaotic system, but I do not take into account the symmetries of the system, mix all the eigenvalues. Eigenvalues from different subspaces, they have no reason to be correlated. No? So you're very much likely to get a Poisson distribution, something close to a Poisson distribution. On the other hand, if you have an integrable model, well, you might have an integrable model with an excessive number of degeneracies. Then you're not going to get a Poisson, you get a peak. Or you may have an integrable model where the spacing is pretty constant, no? The spacing in the spectrum. That's what people call picket fence kind of spectrum. And there again, you're not going to get a Poisson, you may get funny shapes. The extreme case here is like the harmonic oscillator, integrable, but with a spectrum that is super correlated, more correlated than in the case of random matrices. Very well. So I want to call your attention to an interesting model, which is the following. This is the XXZ model that I mentioned before. So it's integral, solved with the beta ansatz. And we are going to add to it a single defect, a single impurity. So I have a single site with a Zeeman splitting different from the other. So this is a tiny local perturbation that you might think should not have much of an effect. But this is enough to give us a Wigner-Dyson distribution. And this is a robust kind of Wigner-Dyson distribution. This quantity that I'm plotting here, this beta, just tells me how close I am to a Wigner-Dyson. Okay, when beta is 1, I have a Wigner-Dyson distribution. So you see that I have a range of values of this defect where I have a Wigner-Dyson. And on top of that, as I increase the system size, that's what this arrow is telling us. As I increase the system size, this range increases. So this is really robust. So according to my definition here, I would just say that this system is chaotic. Now, what is the interesting finding, recent finding? So according to my definition, the system is chaotic, and if it is chaotic, it should thermalize. Chaos is the mechanism for thermalization. I'll come back to this. So chaos is the condition for the validity of ETH. So it's a system that does thermalize, but what has been shown in this recent work is that in fact the behavior, the quantum transport is ballistic. So that comes as a surprise. Usually associate ballistic transport with a system that is integral. So then we have this hybrid situation, if these results are correct, of a system that according to my definition here is chaotic but shows ballistic transport. So this has revived the interest in this model. There is a question. Yeah, go on.
Yeah, so is this like changing the boundary condition of this model in some way, like this?
The boundary conditions here, you could have open boundaries or periodic, it doesn't matter. I'm dealing with open boundaries. And,
yeah, what I'm saying is that, let's say, does this result depend on where you put this defect?
Yeah, so that's what I was going to say now. When I have open boundaries, if you put it right at the edge, then you don't have chaos, and you can solve it still with beta ansatz. But if you put outside any site that is not at the edge, it becomes chaotic. So then you have this hybrid situation, which has called attention to this model. So there are a sequence of studies now in 2020 about this model, which motivated us to put this work in the archive, this Speck of Chaos, to say there is nothing extraordinary about the XXZ model. You can get chaos with a single defect in other scenarios. For example, just pick the easy model in a transverse field. So this is the super simple integrable model. No, you don't need beta ansatz here. And you add the defect, you will get a Wigner-Dyson. And we also discuss a spin 1 model, which is solved with beta ansatz. And again, you put a single defect there and you get a Wigner-Dyson. So these are interesting scenarios. Now the spin 1 is an interesting case to study transport behavior again. And again, robust, okay? So this is that beta that I mentioned before. This is the easy model. As I grow from 12 to 14 to 16 sites, you see the range of that defect value increasing. Okay, so this is the discussion for the level spacing distribution. But I want to call your attention to some more details here. The level spacing distribution, or if you prefer, the ratio of consecutive spacings, which became popular because you don't need to do unfolding. Well, there is nothing so extraordinary about unfolding, no reason to be afraid of it, but okay, this is convenient. So these quantities, they measure just short range correlations. If you want a more complete analysis of the spectrum, should look at quantities that detect also long range correlations, such as the level number variance. So the level number variance is just the variance of the eigenvalues, the number of eigenvalues that we have within a certain interval L. So in random matrices where the eigenvalues are correlated, as I increase this L, the variance grows but fall in this log curve. When the eigenvalues are uncorrelated, then it grows linearly. Okay, so let me show you an example. Here I have a model that is chaotic when this T prime increases. So when T prime is 0.16 or even 0.08, I already see a good Wigner-Dyson. But if you look at the level number variance, well, 0.16 is here, 0.08 is there. So what this is telling us is that the spectrum is not as correlated yet. It's not as rigid as what we have for random matrices. Okay, so this gives us a more general, more complete picture. Another way to study level statistics is via the spectral form factor, and you heard a lot about it today. So let me just repeat the story. If we have a random matrix, depending on its symmetries, you have the joint probability density function. And if you integrate all the eigenvalues, well, let's say 2, then you have the 2-level correlation function. If you integrate all of them but 3, you have the 3-level correlation function. The spectral form factor is the Fourier transform of this n-level correlation function. So you see, the spectral form factor is just a way to study level statistics in the time domain. There is no real dynamics here. There is no information about initial state. There is no observable here. So it's just an analysis of level statistics. The most common one, the most used one, is the 2-level correlation function. And if you look at the Fourier transform, you will see that there are 2 contributions there. One is just the disconnected part, which is just the density of states. In the case of full random matrices, you have the semicircle, and the Fourier transform of that is a Bessel function. But the other part, which is the most interesting one, is the connected part. The Fourier transform of that connected part has been studied in random matrices, and there is an analytical expression for that. What I'm writing on this slide is just GOE, but it could be the unitary or any other kind of ensemble. Now, so here you have all the information, not just short range. You have short and long range correlation. So this is very interesting. This B2 is what you're going to be seeing later in the talk. This is what we have been discussed in a sequence of works about realistic systems, but in the context of real dynamics, not as it's on this slide. On this slide, we only have information about eigenvalues. Okay? Very well. So up to now, we just talked about eigenvalues. What can we say about eigenstates? And again, I'm going to start talking about eigenstates in the context of random matrices. So we are always using these full random matrices as a starting point. We use these full random matrices to guide our studies of realistic systems. Now, this is the scenario of maximum possible chaos in my language here. And then we go to the realistic systems. Now, so the big advantage of random matrices is that we can do things analytically. So it's a good reference point. Anyway, so for full random matrices, all of the eigenstates are just random vectors. No? So big superpositions, these are just random numbers. So we can use different quantities to measure how big the superpositions are, how delocalized the states are. One of them is the participation ratio. So 1 over the sum of these coefficients to the 4th. So here I'm showing the participation ratio for all of the eigenstates of a small random matrix, and you see it's flat, because all of the states are equivalent. They're all random vectors. So this participation ratio is large, it's proportional to D. D is the dimension of the Hilbert space. What comes in the denominator depends on the symmetries of the Hamilton, the random matrix that we are using. Here is GOE, so that's why we have this number 3. So participation ratio is just a number that tells us how delocalized or how complex this state is. You could use different quantities, channel entropy or entanglement entropy. Okay? Now what happens when we move to a realistic system? The first question would be, okay, in which basis are we going to do this analysis now? What the people in the quantum chaos community would tell you, well, pick the mean field basis. Okay, but what is the mean field basis in our spin half models? What we have been using is the eigenstates from the XXZ part, from the integral part of the Hamiltonian. Okay. And what do we see? Well, not all the eigenstates are the same. No? They have different structures. We have this dependence on energy. It's in the middle of the spectrum is where the spectrum is really dense. No? So in these many body quantum systems with two body interactions. And in this region here, then yes, we get very much delocalized states close to random vectors, but not there yet. No? There is always some level of correlations in realistic systems. And at the edges, things are very much localized. So this is one way, a starting point for the analysis of eigenstates via numbers like that, participation ratio, but you can do a more precise, a more elaborate analysis, pick each one of your eigenstates and study those components, like study Porter-Thomas distribution and things like that. But if you want to avoid this discussion of basis, well, a good alternative is move to an initial state. So now you're switching the perspective and start thinking about dynamics. Because the structure, in which basis are you going to study the structure of an initial state? In the energy eigenbasis. So the basis here is well defined. So let me show you an example. Suppose I have an initial state from the unperturbed part of the Hamiltonian. And I add a perturbation, and I'll let this initial state, which is no longer stationary, evolve according to that total Hamiltonian. So let's assume that this total Hamiltonian is chaotic. So the eigenstates away from the edge of the spectrum are chaotic. Let me pick an initial state that has energy close to that middle of the spectrum, so in the chaotic region. And then let's see what happens as we change the strength of the perturbation. So when the perturbation is very small, of course, my initial state is close to one of these random vectors. So its structure will give this distribution of the components of the initial state in the energy, in the eigenvalues would be close to a delta function. Fine. As I increase the perturbation, you'll see that this energy distribution broadens, goes through a Lorentzian, and then eventually becomes Gaussian. So at this point of strong perturbation, where I have this Gaussian distribution, my initial state itself became close to a random vector, became a chaotic state, where these components are very small and almost uncorrelated. Everything that I'm mentioning here is going to get combined when you talk about thermalization. So when will an observable thermalize? Well, let's have a look at the equation that describes this observable. Yeah? So this first term here, it has the components of our initial state. Following what I said, if I have a chaotic Hamiltonian, if I'm thinking about the middle of the spectrum, if I have strong perturbation, well, these components are all very small, uncorrelated, so this will contribute for this term to be very small. How about the off-diagonal elements of the observable? Well, if the eigenstates are close to random vectors, now they are chaotic states, these numbers will be very small. And then we have the phases. If we are talking about matrices, chaotic systems, well, level repulsion. So this at long times will just give us small fluctuations. So on average, this term disappears. And so all that to say that once we are in this scenario of chaotic Hamiltonians, reaching this point is natural, it's almost trivial. Once we reach this point, we have just small fluctuations and we know that they decrease as the system size increases, we say that the system has equilibrated. The second part of the question is now what happens to this infinite time average? We are fluctuating around this point here. Well, if this infinite time average agrees with a thermodynamic average, like a microcanonic ensemble, that's what we would say we reached thermalization. And when would this happen? Okay, so the question is there, when would this happen? ETH, the eigenstate thermalization hypothesis, would tell us that this will happen when, if I compute the expectation values of this observable with one eigenstate or another eigenstate close in energy, and if these values do not vary much, then this left and right side would be very similar. But this has still not answered the question. Okay, we just shift now the question and ask, and when is ETH valid? And the answer is chaos. Now, chaos guarantees all this story. Chaos guarantees thermalization. Chaos guarantees that ETH is valid. Chaotic states. If I have states that are very close to random vectors, of course, if I compute the expectation value with one of them or another one, we have very similar results. So chaos is, as I said, the mechanism for thermalization. In these studies of thermalization, let me just go quickly because I'm sure you have heard about this before. But what do? Study the structure of the eigenstates, as I already said. So here on the top panel, I have that single defect model that I mentioned before. So you see participation ratio is a smooth function of energy. States close in energy are very similar. Integrable cases, large fluctuations. What else we studied? The expectation values of the observables. For the single defect model that I'm saying is chaotic, you see that they all close. You move to the integral, large fluctuations. What else do we study? The off-diagonal elements. The off-diagonal elements in these chaotic systems, they follow a Gaussian distribution. So you can have a number to see how good your Gaussian distribution is, like kurtosis, or this ratio here, the average of the square divided by the square of the average of these off-diagonal elements. If you have a Gaussian, this is pi/2. All of those single defect models that I mentioned before, if you look at that ratio, you get there pi/2, flat, and things only improve as you increase the system size. When you go into the integrable scenario, it's far from that pi/2, so you don't have Gaussian distributions, and things get worse as the system size increases. So this gray here is 14 and red is 20. So you think that things are getting worse. So all that just to repeat what I was saying before. Now we have these super simple models with a single defect, which is chaotic, which satisfies all these conditions used to study thermalization. And yet we have these works saying or discussing that the transfer behavior is ballistic. So that is pretty curious. And
yeah,
then,
I have a question. So does it mean that so without the defect, it's just an integrable model, right? And
yeah.
it will have these constants of motion.
Yeah.
So you lose the constant of motions right away. So there is no exponential, there is no pre-thermal like time scale here.
Okay, so when you're studying a finite system, so it will depend on the size of that defect. No? So if this amplitude is much, much smaller than the interaction strength, then you're not going to get a Wigner-Dyson yet. You go slowly towards that point. And on the other hand, also, if you make a huge defect, then you break the chain in two. There is a region where you do have this chaotic behavior. Now, what those results are indicating is that as you increase the system size, you can make this defect even smaller and smaller. So it gives us the impression that in the thermodynamic limit, an infinitesimal value would be enough, but we don't have a way to show that. But
so
yes,
there is no way to extract some time scales as a function of this defect size and system
we
size.
we do in
Okay.
this work in the Speck of Chaos, we do have some scaling, but the problem is that we have few system sizes to play with. Mm-hmm. So it's not so clear because this system, the Hilbert space becomes huge. Mm-hmm. But the strange thing is that these new studies are saying that this system has ballistic behavior. So how to combine these things? Not that on one side it's chaotic and on the other side the transfer behavior is ballistic. Mm-hmm. But okay, I want to tell you a little bit more about these off-diagonal elements, which is something that we also realize in the Speck of Chaos, which is interesting. Look at this. Remember what I said. Now, if I mix eigenvalues from different symmetry sectors, even if my system is chaotic, we get the Poisson distribution, right? So on this left side, what we did is to pick a model with couplings between nearest neighbors and couplings between second neighbors. I know the system is chaotic, but I also know that it has many symmetries, and I didn't take these symmetries into account. So I look at the level spacing distribution, I get a very nice Poisson. But then we looked at the distribution of these off-diagonal elements of the observables. And what do we get there? A very nice Gaussian, right? As we would expect from a chaotic system. So we get this very nice Gaussian with an additional peak here. And this peak is coming from using the sandwich here with eigenstates from different symmetry sectors, but the shape is still Gaussian. And if I look at that ratio, we get to that flat curve as we had before, and things improving with system size. What changes now is this number. Instead of pi over 2, it's an integer multiple of pi over 2. So this is nice because now we have a quantity, no, which does not require unfolding for those who don't like unfolding. And it detects chaos in the sense that I'm calling chaos here, even if you mix symmetries from different sectors. So that's very convenient. This is nice, you see, because when you're dealing with many body systems, it's not always trivial to identify all the symmetries. And in fact, on the right side, what we have is a spin 1 model, which we didn't know if it was integrable chaotic. We looked at the level spacing distribution, we got a nice Poisson. But then when we went through this more careful analysis, we got to the Gaussian and we realized, okay, this model is chaotic, but there is some symmetry there that we don't know. So this is a nice feature. So it's not just a nice detector of chaos, but it's a nice tool to find symmetry. Okay, but up to now, I only talked about indicators of chaos associated with static properties, spectral form factor, level spacing distribution, eigenstates, observables. How about dynamical indicator of chaos? Okay. This is an important question because like level statistics works very well if you have access to the spectrum. And you do when you're doing nuclear physics. But if you think about this experiment with cold atoms or ion traps, what people are doing there is just studying dynamics. They are not looking at eigenvalues. So is there a way to detect chaos or spectral correlations or whatever we call chaos in the dynamics? And that's what I want to discuss with you now. Now, when you talk about chaos and dynamics, I think what immediately comes to people's minds now is the out-of-time order correlation, now which you already heard about here. The square of the commutator between operators at different times. So what has been claimed is that the exponential growth of this quantity, when an exponential growth shows up, the system should be chaotic. Well, this discussion about exponential behavior, exponential sensitivity in the quantum domain is not new. There were studies back in the 90s about the Loschmidt echo with the same kind of idea. The echo is you evolve the system in one direction and you try to bring it back. This is also a 4-point correlator. And the discussion was also there. If it shows an exponential behavior, we should have a chaotic system. So that's what I want to discuss. Is this a real detector of chaos or not? But let's go step by step. So there were interesting results. Sheridan, Victor, for example, show that with the kick rotor, the OTOC does show this exponential growth in time. There is some relationship between this rate and the classical Lyapunov exponent. There were other studies as well, like Jorge Hirsch's group studying the Decay model, which is an experimental system where you have n atoms collected interacting with the radiation field. Now, so it's a model used to study superradiance. And again, in the chaotic domain, you have this exponential growth with rate connected with the classical Lyapunov exponent. The Decay model has both, has a chaotic regime and a regular regime, and I'll come back to the regular regime of the Decay model soon. Okay, what is the main discussion nowadays was, okay, how about systems? These are all systems with few degrees of freedom. So what happens when you go into a system with many degrees of freedom? And then the discussion goes on. Do we need short range interaction or long range interactions to have this exponential growth? What are the kind of operators that we need? And it's all an interesting discussion, which I'm not going to go into. What I'm going to say here is just what I've done with Borgonov and Israelev, which is an analysis for many body quantum systems, but not of the out-of-time order correlator. We are looking at participation ratio, but not this participation ratio that I mentioned before, which is just a static thing associated with one eigenstate, a dynamical kind of participation ratio. So what is the idea? I prepare my system in some many-body state and let it evolve according to a total Hamiltonian. Well, this many-body state will be visiting many other many-body states in this huge Hilbert space. So what we call participation ratio here is 1 over the sum of the square of these probabilities. So the probability for finding this initial state in any other of these many-body states. If you want to make a connection with the OTOC, what you could do is the following. For these operators, W and V, use projection operators. So if you do that, each OTOC that you get in this way is one of the terms in this sum. So this would be, this participation ratio would be the sum of this projection kind of OTOCs. For each one of these projection kind of OTOCs, you do not have an exponential growth, but if you sum them all, then yes, you do have an exponential growth, where this rate is given by the width of the energy distribution of the initial state that we selected. So this we did for spin systems and also for the two-body random ensemble.
Sorry, Lea, what is this state that you actually select? What's the initial state? Yeah,
so the initial states are initial states from the unperturbed part of the Hamiltonian. So in the case of spin systems, it could be, it's that mean field part of the Hamiltonian that I mentioned before. Okay, so I have one Hamiltonian here. So the initial state is an eigenstate of this part. And initial states that have energy in the middle of the spectrum, because that's what chaos is. Is this fine?
No, I'm just asking. Yeah,
okay, I just, it looked frozen, so I didn't know if you were speaking or not.
Oh.
Okay, so anyway, so this is the discussion that we have for many-body quantum systems. We do have this exponential growth with the rate given by the width of this energy distribution of the initial state. What is the initial state? Is the mean field part of the Hamiltonian and with energy in the middle of the spectrum. Now, there are many other things that are interesting to go on into this discussion, like how to connect this rate with a possible Kolmogorov-Sinai entropy, and I'm not going to go into this here. I just want to come back with this discussion of the OTOC. Is this a detector of chaos or not? Let me make my question more precise, because some people complain about it when I said it this way before. What I'm asking is the exponential growth of the OTOC at short times a good indicator of chaos, or what we are calling quantum chaos? And why I'm asking that? At short times, what happens to the system is very much related to whatever is happening to it in the classical limit. In the classical limit, you can have a regular system, okay, not chaotic. You can have a regular system with a positive Lyapunov exponent. Typical case, a simple pendulum that is inverted. You get a positive Lyapunov exponent just because you are at this unstable point, but this has nothing to do with chaos. You don't have mixing here, okay? So what the group like Jorge Hirsch did, and the other groups that I'll mention also did, Jorge Hirsch did was, let's pick a model that is regular. So they looked at the decay model in the regular regime. But let's look at it right at the critical point for the transition between a normal phase and the super radiant phase. So right there, you do get an exponential growth for the OTOC. And this rate is connected with the classical Lyapunov exponent. But this classical Lyapunov exponent has nothing to do with chaos. It's only indicating instability, okay? There is no mixing. This was also done for the Lipkin model. The Lipkin model, you know, it's completely integrable. But right there at the critical point, you do get an exponential growth. Again, rate connected with the classical Lyapunov exponent, which is not telling us anything about chaos, is a reflection of instability. At the time that Hirsch was doing these studies, other people came up with the same idea. So this work here is by Fazio. The second work is Klaus Richter. This is Kao. This is Hashimoto. all studying different kinds of regular systems, but with unstable point. So then, to answer my question, I would say that OTOC is a good indicator of instability at short times, not necessarily chaos. All right, so the question is still there. Is there any kind of a manifestation of chaos in the sense of spectral correlations in the dynamics? And the answer is yes, but you need to wait a little longer because you need to give time for the dynamics to resolve the discreteness of the spectrum. Once it resolves the discreteness of the spectrum, it will realize if this spectrum is, if these eigenvalues are correlated or not. If it is correlated, we'll see it showing up in the form of what is known as correlation rho. Okay, so what we are going to do is study this quantity, the survival probability, and here we are really doing dynamics. Okay, so survival probability is the probability for finding the initial state later in time. Very simple idea. And I'm going to prepare my system in an initial state such as this one, spin pointing up or down in the z direction for the spin system. So it's the kind of initial state that an experimentalist could prepare, someone work with ion traps. That's the kind of state they have, or cold atoms. Okay, so we are always in close contact with the experiment. And so I can write the survival probability in terms of the sum of those components of the initial states. These components are coming from this quench dynamics. Of course, if you're doing things theoretically, you could put whatever you want there. You could put a constant. If I put a constant here, I would be going back to the idea of the spectral form factor. Or you could select these components from some smooth function, or you could put Boltzmann factors there. So these would bring you closer to those discussions of the analytic continuation of the partition function. We are not doing that, okay? We are in touch with the experimentalists. Those components are coming from a real kind of initial state. Whereas we have the phases with the eigenvalues. So there was a question before to Victor about, do we unfold the spectral form factor and so on? We are not going to do anything to these eigenvalues. No rescaling, no unfolding, no nothing. Remember, I'm thinking about the poor experimentalist who is not looking at eigenvalues. The person is just studying dynamics. Okay, I don't touch that. Okay, so, and then what do we have? I can also write this sum with an integral. Now, where this rho here is just the sum of those delta functions. So this rho here is just an energy distribution. But it's an energy distribution weighted by those components of our initial state. So it's the energy distribution of the initial state, what I mentioned before, that we usually call local density of states, LDOS. Remember, I showed you a picture before about this energy distribution, where I was saying, as I increase the perturbation, they think this distribution gets closer and closer to a Gaussian. Middle of the spectrum, chaotic Hamiltonian, strong perturbation, this is close to a Gaussian. Well, what is the survival probability? Just the square of the Fourier transform of this energy distribution of that particular initial state that we have. Fourier transform of the Gaussian is just a Gaussian. So we start with this Gaussian decay, but if you wait a little longer, well, the spectrum is bounded, so you will develop a power law behavior. All up to this point, we only have information about the envelope, the shape of this distribution. But how about if I go a little longer? If I go a little longer, is what I was telling you before. Now, we give time for the dynamics to realize that we don't have just envelope. We also have what is inside. Now, the eigenvalues are discrete. So once it resolves the discreteness of the spectrum, that's when we are going to pick up the correlations. So we have these two contributions that I already mentioned before when I was talking about the spectral form factor, shape of the distribution, which is not that interesting. The interesting part becomes with the connected part, the correlations. So remember what I said, that connected part, the Fourier transform of that is described by this B2 function. Okay, so let's now look at the entire evolution of the survival probability. Here you have the whole thing. for a realistic system, for a realistic kind of initial state. So initially Gaussian power law. At very long times, saturation of the dynamics given by those components of the initial state. What do we have in between? We have this dip below the saturation value. That's what is known as correlation hole. Now, this was studied by the quantum chaos community in the context of molecules. This is what is now called, well, this correlation hole is the part described by the B2 function. It's picking up the correlations.
Yeah, this is for randomatics, yeah?
No, this expression here is for random matrix. Yes, this is what you get like in Meta's book, but this plot here is for a realistic system, but it's a realistic system that has the spectrum, the eigenvalues are almost as correlated as in full random matrices. So for this realistic system, I can use the same B2 function to describe it. Okay. Just like in a realistic system, I can also describe the spectrum with a Wigner-Dyson distribution or the level number variance from random matrices.
But Lea, if you don't do unfolding, you won't exactly see this function, right?
Oh, no, you don't need to do any unfolding. That's the whole point. You don't need to do any unfolding. You will get that. What you have to be careful, and I'm going to tell you this, you have to do averages. But wait a second, I'll come back to that. So, so if you don't believe that, go on and do it, because it's very simple. There is no need for unfolding here. But so this dip, that's a true direct manifestation of correlations in the spectrum. What happens before, that has nothing to do with what I am calling chaos here. This has to do with the strength of the perturbation, the initial state that you picked, not chaos. Chaos is here.
Yeah, but you have some range of time where you have exponential decay. Is this, can you detect this exponential decay?
Yeah, this is the thing. For this system, this is a spin system with on-site disorder where we are doing big averages. We never found the exponential behavior. If there would be an exponential behavior, it would be between the power law and the Gaussian.
Yes.
We don't see that. We have this Gaussian distribution, so we go Gaussian decay and power law. Now we don't get exponential. Now, what else was going to say? Now, okay, so this correlation hole, it described like this, by this function from full random matrices, will only show up in chaotic systems. Now, careful, you can have a dip like this, also in some integrable systems. Remember that I said that there are some integrable systems where the spectrum is very much rigid, like the harmonic oscillator. So you would get a dip like that, but it wouldn't be described by this B2 function. Okay? Now, this hole is what is now known as ramp. Now in many studies in high energy physics, because you have this growth to the saturation point. For the GOE, it is initially linearly. Once you get very close to the saturation, it's not linearly anymore, it's quadratic for GOE. Okay? But anyway, so some details about the hole. As I said, for all of these systems, where you have eigenvalues with correlations similar to random matrices, such as those single defect models that I mentioned before, you will have the hole showing up with the shape given by that B2 function. What is nice about the hole, you don't need to do unfolding, so I repeat that. Nice thing, you don't need to separate the states by symmetry sectors. You will detect it. Okay, and also nice, it's a true dynamical quantity. What are the issues with the hole though? First thing that you could ask, since I'm trying to be so close to experimentalists, you could ask, but can an experimentalist really detect the survival probability? I'll leave this for them to answer, okay? But we already know that even an observable, local observable that is currently measured can detect the hole also. So this plot that I'm showing here is for the spin autocorrelation function. So what it tells us is how close our spin configuration at a certain time is to the initial spin configuration. So this is equivalent to the density imbalance that is measured in cold atoms. This quantity at long times shows a behavior that is very similar to the survival probability. Both are autocorrelation functions. Okay? This is the spin autocorrelation function, and this is the autocorrelation function. So they both develop this correlation Hall. Okay, so this is for the question about observable. The other issue is the averages that I was telling you before. In the region of the Hall, these quantities are not self-averaging. What does that mean? You have to do averages, no matter how large the system is. Any kind of average you prefer, average over disorder realization, average over initial states, running averages, any of these will give you the whole. If you don't do averages, you'll have big fluctuations here that will cover the whole. Okay, so you just have to do averages. Now, for the survival probability, there were some discussions about lack of self-average. Well, it was not for the survival probability. Discussion about lack of self-average of the spectral form factor. And you see that the spectral form factor is contained in the survival probability. No? So using full random matrices, what we showed in this work analytically is that the survival probability, not just the whole, but the entire survival probability is non-self-averaging, which just means that you have to do big averages, okay? But it's a nice result that, again, is coming from the help of random matrices, that we can show that the entire evolution is not self-averaging. But, okay, what is nice about the survival probability is such a simple quantity that we can get things analytically. Okay, so here we have the analytical expression for the evolution of the survival probability under full random matrices, so the entire evolution. So here in black, we have this expression, and in red, the numerics. It's just the opposite. In red is the analytic expression, in black is the numerics, and you see perfect agreement. On this right side, following the same steps that we use to derive the expression for random matrices, we derive an expression for realistic many-body systems, systems with two-body interactions, chaotic systems with two-body interactions. And this expression here is shown with this dark curve, and the numerics is in red, and you see perfect agreement. Now this is log-log. So
sorry,
yeah, question.
What is capital D?
Capital D is the dimension of the Hamiltonian.
Okay.
So what do we have here? At short times, okay, at short times, the behavior for full random matrices is not the same of the behavior for realistic systems because of that energy distribution, which is not the same. But at long times, all we care about are the eigenvalues. From this point on, where we have the correlation Hall, the dynamics is the same for random matrix and for realistic systems. So from then on, we picked up random matrix properties. And then we'll finally saturate. Now, what is nice about this is that if we have an analytical expression, we can get the time scales. That was our main interest going back to the beginning of the talk. The time scales for the relaxation process. What are the different behaviors and the time scales associated with each. And now we can do this analytically. So the first important time scale is this, for this decay here, is 1/, gamma. Gamma is the width of the L dot, remember that? So 1/, gamma gives us this depletion of the initial state. The other time scale is the time to reach the minimum of the whole, where everything becomes just pure random matrix. This time here comes from where these two functions meet. Now the power law decay going down and the B2, the ramp, bringing us up. So when the two meet, that's what this time, which we get. And then finally the time for the saturation. So what do we have? For random matrices, the time for the minimum of the whole is just constant, of course. For the realistic system, this time grows exponentially with system size. And why? Well, we start with an initial state like this, which has an exponentially large number of many body states to visit, but it does that with local two-body couplings. So it takes an exponentially long time. to visit all of these states and forget about that initial state and then just detect correlations between eigenvalues. And so it grows exponentially. So we got this analytically. This is what we are calling Thouless time, because beyond that is just random matrix theory. And the other time that we also get analytically, the time for the saturation, well, that one is just the inverse of the mean level space. Question? No. Inverse of the mean level spacing, which is the largest possible time scale of the system, is the Heisenberg time. Dashed line is Heisenberg time. This is red is the time to reach the minimum of the whole, and the symbols are numerical results. This is what we have. Let me see the time. This it's already 14. So Sheridan, how is it? Should I stop?
No, continue. So you started around 3:30, so you have like 5 to 7 minutes more.
So, but I'm going to wrap up. So, what I talked about before, survival probability for the chaotic system, is all analytical results together with numerics. In this work, we have many other numerical results. For observables, several interesting results, but it's just numerical. And for the survival probability, we also studied it for this Hamiltonian as we increase the disorder strength. So as we increase the disorder strength, we move away from the chaotic limit and we approach in localization. As we increase the disorder, we'll be killing the correlations. And so you see that that minimum of the whole is going to get postponed. And we study that numerically and see that the time to reach the minimum of the whole increases exponentially with the disorder strength. But this is still numerical, but we are at the verge of getting analytical expressions also for these intermediate regions. Okay, but this will come up soon. So, but let me conclude. What it is to be done is to get these analytical results for this intermediate region, and we are about to get that. And of course, we would also want to get analytical results for other local observables. But an important message of this whole story here is how useful random matrices are. Now, even though they are not realistic, we use them first, get analytical results there, and then use it to guide our realistic studies of our realistic systems. So with the random matrices, we got an analytical expression for the survival probability. We got an analytical expression saying that the survival probability is nowhere self-averaging, and all that then helps the studies of realistic systems. Just one more thing about the other work, the Speck of Chaos. No? So there you are, you have this simple model with a single defect that is chaotic according to my definition, and yet some new results are showing that you have ballistic transport. So how to make sense of these things. And in this work, we also discuss two indicators of chaos that I find very interesting, the correlation hole and those of diagonal elements, why they are so useful. You don't need to do unfolding, you don't need to care about the symmetries. The correlation hole on top of that is dynamical. So they're not just nice indicators of chaos, but they are helpful tools in the search of symmetries and in the search of integrable models. Okay, so I'm going to stop here and thank you for attention.
Thanks, Lea, for the talk.